May I request you to please settle down so that we can get started with the first session. And welcome to track 1, day 1. We have an impressive lineup of speakers. So in the first half, we have 2 tutorials. So both of them belong to the analog and device physics theme. So our first tutorial will be given by Professor Dasgupta, Professor Sudeb Dasgupta, and Dr. Navjeet Bagga. So allow me the opportunity to introduce our speakers. Professor Sudeb Dasgupta is working as professor in the Department of Electronics and Communication Engineering at IIT Roorkee. He received his PhD degree in electronics from IIT Banaras, Hindu University. And during his PhD work, he carried out research in the area of effects of ionizing radiation on MOSFET. Professor Dasgupta had earlier served as faculty member at ISM Dhanbad. He tenured as the head of department at IIT Roorkee during the period 2019 to 2022. He has authored and co-authored more than 300 research papers in peer-reviewed international journals and conferences. Professor Dasgupta has received multiple awards and fellowships during his long career, including Erasmus Mundus Fellowship at the European Union, the prestigious IUSSTF to work at the University of Wisconsin at Madison, DAAD Fellowship at TU Dresden, Germany, and many more. His area of interests are nanoelectronics, nanoscale, MOSFET modeling, and simulation, design and development of low-power novel devices, FinFET-based memory design, emerging devices in analog design, and design and development of reconfigurable logic. He has guided 18 PhD scholars. Currently, he is supervising around 6 candidates leading to their PhD degree. Dr. Dasgupta has acted as reviewer for multiple IEEE journals and has also been member of technical committees of various international conferences. And as a personal note, Dr. Dasgupta was the tutorial chair of VLSI in the previous version. Thank you, Dr. Dasgupta. I'd also like to introduce Dr. Navjeet Bagga. Dr. Navjeet Bagga is currently working as an assistant professor in the School of Electrical and Computer Science, IIT Bhubaneswar. He received his PhD from IIT Roorkee in 2019. He has worked as a postdoctoral fellow at Karlsruhe Institute of Technology, Germany. Before joining IIT Bhubaneswar, he has worked as assistant professor at PDPM IIIT DM Jabalpur. His research interests include semiconductor device modeling, self-heating, and reliability aspects of nanoscale devices like nanosheet FETs, FinFETs, Hochsheet, negative capacitance, FETs, tunnel FETs, and multiple such devices. He has authored and co-authored more than 90 papers, and he has received 3 Best Paper Awards at IEEE international conferences held in Europe, Kolkata, and Bangalore. He has actively collaborated with his national and international peers in the semiconductor domain. He is a senior member of IEEE and a life member of IETE. He is serving as an editor of the Journal of Electrical and Electronics Engineering and a reviewer of many journals and conferences. Welcome, sir. Thank you. We would like to please give me please welcome our speakers.
Can we have this maybe lowered down? It's hitting my eyes. At least this one. Okay. Good morning, all of you. Again, it's an honor to present in front of such a wonderful set of people, students, faculty members, organizers. And since I have been the chair of this VLSI 2024, I know what goes behind before we end up in this stage. So thanks a lot, Gaurav, and everybody here. So with this, let me start today's tutorial. And this tutorial is primarily on multi-stacked, more emerging devices. And the reason for giving this tutorial was, or presenting this tutorial was to showcase to you what are the various options in terms of devices available to us in post 2030, 32 around. So these are the table of content which we will be looking into. We will be introducing the lecture and then we will go for FinFET. FinFETs are already well defined. Many things have been already done. There are certain issues in FinFET which still remains a challenge. So we'll go into that and then we'll moving towards the stacked transistors here. And then one specific work which was done at my group was high frequency modeling of these devices and their circuit implications. And then we will go for resistive and capacitive modeling. The idea here is when you do a RC modeling, you need to find out the frequency of operation of the device, and that's the reason this is important. This slide, all the device people show, right? In the first slide, they show it. And the reason being very simple and straightforward. If you look at the trend here, post 7 to 6 nanometer FinFETs tend to have problems because of their quasi-planar structure. They tend to have problem. What has come to the rescue is sort of a GAA devices, gate-all-around devices, within which we have nanosheets devices as such. Post 5 nanometer, we do have fork sheets coming up from IMEC Belgium. We are not very sure whether this will come up in a big way or not. Industry is still not accepting it in a big way. But nanosheet is coming up in a big way. And we would expect to see CFETs coming up, complementary FETs coming up post 2032, 31, 32. We would expect to see this coming up. A large amount of work is going on in the CFET technology. And that's what is written here, right? And therefore, FinFETs are saturated beyond 7 nanometer and 5 nanometer. There is a big amount of work also going on having the channel itself being converted to an atomic channel, where you, rather than having a 1D material, you can have a 2D material with ultra thin body, by which you can formulate a current flowing through the CFET to a very large extent. CFET gives you an advantage about the area. For the same area, you get almost double the functionality in CFET, right? And I will come to that later on. This is the graph which many of us use, showing you the switching energy versus the year in terms of year. And as you can see here, the energies are actually going down when you do hyperscaling in this case. Now, we already know this, so I will quickly go over this, but let's see how it works out. If you look here, this is quite interesting. This is the first time beyond MOSFET, right? MOSFET was being developed in 1925, Lilienfeld patent, and it has still hold good for us. But what has happened is, this was the first time when you did have really a three-dimensional structure being formulated, which means that your source and drain, so this is drain, this is source, and this is sort of raised structure. And this green colored is the gate in the FinFET, right? However, it has got low leakage, it is a 3D structure. However, there's a challenges of fin height. You do have a problem of higher source and drain resistances, because the resistance becomes so high, contact resistances are becoming so high because of its three-dimensional nature, that the amount of current which you gain out of it becomes relatively small, right? And obviously all of you are aware of width quantization is a major issue in a FinFET. And they become a layout dependent issues. Below 28 comes out to be a big issue. Similarly, if you look very carefully, this is made on a 111 plane, and this is made on a 110 plane. So there's a reduced mobility also comes into picture here. Now let's move to from nanosheet, right? We move to emerging stack transistors, right? Now, if you have any questions, any point of time, let me know, because this is a 45 minutes tutorial. I won't be able to give you all the ideas, but just a brief idea where we are moving ahead. Now, if you look very carefully here, this is what we are looking into nowadays. We have these nanosheets here, and this is the gate which is surrounding the whole channel. And you have 1, you have 2, and you have 3 sheets, and you have source on this side, the drain is on this side, right? And as you and the gate is responsible for forming the inversion layer at this particular point. But I hope you appreciate this point. Unlike bulk MOSFET, in a FinFET or in a nanosheet FET, since it's a 3D stacked layer, you end up having a larger capacitive and resistive issues coming into picture, which means that there will be heavy intersheet coupling or intersheet capacitances, which will which will enhance its capacitance. But once it does that, you do have a problem that its current will also become larger, because you are using 3 sheets to develop the current. This was developed by IMEC Belgium in IDM paper, IDM edition, I think 2022 or 21. IMEC Belgium researchers, what they did was they made this as a gate, this is source and drain, and this is the dielectric wall which they put. So this was N side, this was P side. And this is the fork sheet FET. What happens in CFET is, in CFET you have PFET at the below and NFET at the top. So your area actually reduces, and you are able to generate an inverter, CMOS inverter, in a sense very easily through this methodology, through this CFET. Easier said than done, but that's what we are looking into currently. And as you can see, CFET improves performance by increasing the width. So as a designer, device designer, or a circuit designer, your knobs to play with is basically the width of this nanosheet and the distance between these 2 sheets. If you increase the width, simple, ID equals to mu n into C oxide W by L VGS minus VTH, 101 device physics, right? In that, if you simply increase the value of W, automatically your current will increase, right? So that you just simply increase this high value and you automatically get a larger current, which is very straightforward and simple way of looking into it. Now, since we have understood FinFET, given you a very brief idea about nanosheet FETs and fork sheet FETs, we possibly won't go into details of fork sheet FET, but we'll go into details of this high frequency modeling. The requirement came to us from an industry partner of us, where they told us that we need to form a multi-gate. So we need to actually work on nanosheets FETs for very high frequency applications, right? Typically for 5G, 6G applications, they told us they would want to do it. And that's where we were looking into at this stage. So we did a small signal modeling of FinFET. So we took a FinFET and we did a small signal modeling, we did a small signal modeling here. And I think all of you are aware of this particular point. How do you do a modeling? What you do generally is this blue colored, this dotted line which you see here, this is the intrinsic part of the device. So this is the device internal intrinsic part, and this is the extrinsic part which you see here. So I have a gate resistance, I have a drain resistance, I have a source resistance, and I have fin resistance. So if there are multiple fin available to me, there will be multiple RC elements. So if you have 1 fin, 2 fin, 3 fin, then you will have 3 resistances in parallel, and there will be 3 coupling capacitors between them, right? Very straightforward and simple to look into. So that's what I have shown you here. So there will be resistances and capacitances. There will be resistances and capacitances here, and so on and so forth. I do a parameter extraction. Then we do, this is geometry independent, mind you. And that's where the wonderful part of small signal modeling comes into picture. That it's geometry independent. So meaning that you don't have to worry at this stage, early stage of modeling, that what are your goals? You just need to take up that FinFET and plug it here, and you should be able to do it. These are all two-port networks which we do. Simple two-port networks. Nothing extraordinarily difficult to handle. And that's what we did. And this was published in paper, but this work was done by Jyoti, my research scholar, and she is currently working in UMC in Singapore. And what we got was, so this is how, so we did a cold fit approach. So whenever you do a modeling, right, those who are doing modeling, device modeling, they will, there is a cold fit approach. Cold fit approach basically means you take the intrinsic part, don't give any bias anywhere, right, and simply check what is the value of the resistances and capacitances internally. That's what is a cold fit. So you don't give any DC bias at the gate or drain side. Am I clear? Right? When you don't give any DC bias, obviously, you don't have any current flow. Right? I'm not interested also to look at the current flow at this stage. I'm just interested to look at what is the typical value of the resistances and typical value of capacitances at particular point. I can also do a transient analysis, which means I can give a short pulse and check what is the capacitance and voltages at particular point. These are all done we did it on a MATLAB platform, but typically, so this is how do you find out is basically, if you look very carefully, this is basically a y is equal to mx plus c sort of straight line formula, extrapolated backwards, and you would be able to extract the value of RS and CE and so on and so forth. So this is sort of it's a quasi sort of methodology. Means you extract it, this is not an experimental, extract it, plot it on a graph, extrapolate it backwards, check the value of Z1, Z2, Z3, and then plug that value of Z1, Z2, Z3 here to get the value of Z external. Once you know Z external, you don't have to worry about anything else. Your job is done as a designer. Right? Okay, so we did a NQS models so I think NQS model is what does it tell me is that I assume that, so NQS model is something like this. If I have this device as a MOSFET, then I assume that a finite amount of time will take place for an electron to move from source to drain if I apply a bias. When you do a quasi-static model, it is instantaneous movement from electron from this to this. So this is the difference between NQS model and a QS model. This model is obviously more complex because there's a distributed resistance between source and drain, and therefore you need to find out the Y parameters in terms of circuit elements, which you find out. So this we have already calculated from our previous slides. ZGSN is gate to source for N MOSFET. This one. This CGDN, ZGDN is impedance, gate to drain impedance of N MOSFET. So once you know these values, just plug these values and you get Y internal, right? Intrinsic. Once Y intrinsic is known to you, you just have to take that as a black box and use it everywhere, wherever you want to use FinFET. Are you able to get the whole idea how I'm using it? So I take a black box approach and go on fitting this black box. Now you tell me, I am using a 3-fin device. No, let me use a 4-fin device. No problem. I will just go back to my initial model, make it 4-fin. New value of Z and Y parameter will come into picture. Plug it, take the value of Y intrinsic and carry forward. Okay, this is what we got at our, and we matched with TCAD. We matched this with TCAD approach as well to a larger extent. And we validated our Y parameters with TCAD. Now that is what quite interesting is all about. Now what happened if you look very carefully, if you look at Y11 parameter, there was perfect matching between the TCAD, conventional model and modified model. And that is what I wanted to stress. That our model was even valid beyond 100 gigahertz, right? Again, please take this with a pinch of salt. What I am saying is not absolutely correct. When you actually fabricate this FinFET on silicon, things will be quite different, right? So please don't take this. But surely, with the methodology which we have done, we will get more than 100 gigahertz of frequency for Y11 which we get. Same thing happens for real value of Y11 and so on and so forth. However, if you look at this particular graph, I will tell you what the real value of Y22, the green one has actually flattened off. This is frequency and this is real value of Y22. The green one, which is the conventional one, is not able to capture the beyond high frequency, beyond 100 gigahertz. It's not able to capture. But our model was able to capture that one. And that's the reason you can see it here. This transconductance and capacitance which we got for various temperature, and this was the requirement from the industry or otherwise, was that you required to have a large temperature range. However, we are working on it still, and it's still working on it. And as you can see here, the transconductance actually falls down drastically beyond 100 gigahertz, right? And the GM actually falls down. The red color is the GM. This is gate to source and this is gate to drain, right? The gate to drain and gate to source almost remains constant, independent of the value of the frequency, right? And there's a reason for that, very standard reason. But transconductance starts to fall down beyond a particular point. And that falling down of transconductance takes place because beyond the frequency, so look at it in this manner, in a very layman language. If you are actually increasing the frequency of operation beyond a particular point, the electrons will not be able to react to those changing frequencies. And therefore, del GM, which is del ID, del VGS, will actually fall down. And that's what is happening here in this case. Now, let me come to the, so this is quite an interesting study which we did. Now, if you remember, I was just discussing with you, so I don't know, I don't think I have told you, but this, let me show you where is the FinFET. Right, this is the height of the fin, right? And this is the thickness of the fin. This is the height of the fin, this is the thickness. Now, if you have multiple fins, 1, 2, 3, then this between this edge and the center of the next fin is defined as my fin pitch. So there are two very important parameters in FinFET. One is the fin pitch, which is the difference between the distance between the two fins, and another is the height of the fin. So effective W is 2H fin plus 1 T silicon. You see? This is the effective W is this plus this plus this. I hope you understand, right? And therefore, if you go back to my, so what I was discussing with you just now, sorry. So if you look back here, you see, as my frequency goes on increasing, this is my zero unity gain which I get. So this is my FT at 427 gigahertz I got. Fmax was 625 gigahertz which we got. However, this is very, very important as a designer, that your H fin by S fin was approximately equals to 1, which means the height of your fin and the separation between two edges or the two fins were both equal. You will ask me, why is it important? Obviously, it is important. Why? Because if you keep the separation very large, you end up having a larger area. If the separation is very low, you end up having a larger capacitances. So you pay the cost of having large changes in both the cases. So a very optimized value of H fin by S fin is very important, and that's what I have shown here also, that for 1.05 H fin by S fin, for S fin equals to 40 nanometer, I get a Fmax of approximately 600 gigahertz. Right. Now, this was a problem statement which I think Jyoti worked with Navjeet, and we all worked together on this one. And this was what we did was, so the idea is, when you're working with fins, since it's a quasi non-planar structure, and there is a length dimension given to it, there will be distributed resistance occurring, right? So it's almost like an interconnect, long interconnect, and there will be R1, R2, R3, R4, R5, so on and so forth. C1, C2, C3, C4. That's what I've shown here. So this is RH, horizontal resistance, and this is vertical resistance. This is source drain. This is obviously width, and the fin I've already told you. So what we found out was that, quite interestingly, and this was for the first time to the best of our knowledge we were able to show it, that when we were able to calculate this, these were highly geometrical dependent. Obviously, they were very geometrical dependent. And therefore, please understand, when you apply a bias here, the same potential will not be visible to all the three fins. That's where the variability comes into picture, right? And that's the problem area which you will face. And what we found out was that when the number of fins was 2, your gate resistance was minimum. And when the number of fins started to increase, the gate resistance again shot up. And we don't want this to happen. So we limited ourselves to 2 numbers of fins in all practical purposes. This was a study which was done by one of my intern who was also working with Navjeet at IIT Bhubaneswar, and he came to us to work. And this was quite interesting. The interesting part was that if you look here, if this is the FinFET, then this is the top gate, right? This is the side gate. And if you take all the 4 sides, this, and this, which means that if you make a contact just at the top, and if you make a contact just at the top and this side, and if you make a contact just top and back, then the value of the current which will be flowing through the device will be quite different. Very simple. You take this, you have a contact here. Rather than having a contact here, I have a contact here also. So I have a better contact. I have a less amount of resistance available to me, higher amount of current will be available to me. Very straightforward and simple. That's what we did. And we used a conformal mapping technique. Conformal mapping is, so you remember capacitance, Gauss law? Everybody knows Gauss law, right? So Gauss law, when you calculate capacitances, you calculate capacitances, the parallel plate capacitances which are separated like this. But if the plates are not perfectly parallel, but they are horizontal in nature, for example, this, or this, or this, or any shape, then we use conformal mapping to find out the value of the capacitance. That device modeling people use quite a lot. And we used that and we found out some resistance. This was done by, this was from this paper which I am showing, but this was done by one of my students as well. Now this was the resistive modeling of stack transistor. Now you see, this is where now we are shifting from FinFET to nanosheet. Now nanosheet is, this is source, let us suppose this is drain. This green colored is my channel here, sheet, 1 sheet, 2 sheet, 3 sheet. There is a very good paper by Louvet, Louvet. Those who want to work in this domain, that's the only one paper available till today to the best of my knowledge, where you have an experimental validation of a 3-stacked nanosheet FET experimental value, from where you can actually do a TCAD calibration. There might be other things also, but that's what I perceive. We found out this split resistance. So we did a research, we did a work on this, and we found out the contact resistance, and we found out the split resistance given by this and T sheet. T sheet is the thickness of the sheet, this sheet thickness, and this. So it's very, very geometry dependent, and that's where Professor Bagga will be presenting in the next talk, reliability issues, right? Okay. Now this is okay. Sorry. So this is how you actually do in resistive modeling. When you do, you break it up into two parts. One is RPN here and RPN here, and then what you do is that so you go from RPN1, RP2, RP3, and so on and so forth, and then you go RP1, RP2, RP3, RPN minus 1 till RPN. You see? You break. So these are all sheets. One sheet, two sheet, three sheet, four sheet, and so on and so forth. And for every sheet which you see, you will have two resistances. One coming from the source side, another coming from the drain side, right? Now the problem is, I don't know how many of you are aware of, but typically MOSFET, though is termed as a symmetric device, it's not actually a symmetric device. Same thing happens for a nanosheet FET. Because in the drain side, the charge sharing is not symmetric in nature. Remember? The charge is more towards the drain side as compared to the source side. So since the charge sharing is not symmetric, you will never have the resistance being symmetric nor the capacitance being symmetric. So what we do, we generalize it by writing this formula here. Then we go for the capacitance modeling, and this is where it becomes a bit complicated. And the reason it becomes complicated is not because we want it to become complicated, but we don't have any other option, because it is now becoming a three-dimensional stacked structure. Till now, FinFET was three-dimensional, but at least it was a single layer. Now the first time you have this stacked structure available here, right? And you do have a problem of this. So what will happen is, so you see this. This is my source. This is green color. There might be like this. There will be electric lines of forces which will emanate. So there might be some capacitance here. So it is something like this. There will be capacitance between these 2 points. This capacitance you will never find for other devices. Here, since it's a quasi-planar three-dimensional device stacked layer, right? You will always find this capacitance into picture. That's what capacitance you can see here, this one. So you have multiple capacitance as you can see here, and these are multiple contacts which you see here. And from here you can find the values of the various capacitance. We were able to find the value of CGS, and the results were quite interesting, and they gave us almost the same value of simulation and the model result. Now, let me come to intersheet capacitance for NSFET. So intersheet is basically between this sheet and this sheet, right? Between this sheet and this sheet, we have intersheet capacitances. So if you lower it down, so generally, why do you study intersheet capacitance is, when you fabricate nanosheet, for that matter, anything else, always there will be a process variation, right? These process variation will tend to make the sheet distance either go low or high. So if you have an a priori a model defined where you can actually tell me the value of the intersheet capacitances even before it is fabricated, that will help me to do it. And that's what we try to do here in this case. So we try to find out the value of all these values and plotted it against a graph. Now, what we also did was we tried to make this we tried to make it asymmetrical in nature. This and this distance. So once I make it asymmetrical, and this is quite interesting, what happened was, when I make it asymmetrical, the intersheet capacitance actually around 0.2 volts, it actually saw a sudden rise. We are not very sure why this happened, but this is again a TCAD and model. So we are not very sure why it rises and then falls, but around 2 volts it suddenly rises and then it falls down to a very, very low value, almost 0.02, 0.03 value somewhere here in this case. However, the good part was that the symbol and the model were matching very well for all the reasons. Right. Now, let me come to nanosheet FET performance and small signal modeling. And maybe what we can do is, so what we did was we took up this Louvet paper, calibrated our NS FET And we took this calibration, this parameter value, and then we used the nanosheet FET, and we calibrated it and matched properly with TCAD and experiment. And then we tried to find the value of the transconductance, current, and so on and so forth. Correct? And as you can see here, quite interestingly, ion by I-off ratios for NSFET were relatively larger as compared to that of FinFET for the same value of the gate length. And this is to do with both the sides, both ion increasing and I-off decreasing, right? Ion increasing because you have multiple sheets. If you have multiple sheets, you have multiple current. So current will increase, ion will increase. And I-off decreases because you have much better leakage. You have much lesser leakage available here. Now, the question which we found out, or not we, but the question which researchers are trying to find out is that if I consume lesser amount of power, can I achieve the same performance? That's the whole crux of the game as far as NSFET is concerned. With the same amount of power as FinFET, can I achieve the same amount of performance? Right? And that's more so, things are now coming up in a way where things are matching up. Yes, this can happen. FinFET is a very mature technology. All of you must be aware of this fact. Right? NSFET is still not. NSFET, many things are unanswered till now. In fact, FinFET also many challenges are there. However, I want to show you one important result here before we move forward. If you look at VGS versus Fmax, around somewhere here, around 0.6 volts, if you look, you see that your NSFET actually starts to fall down, your Fmax falls down when you operate at very large values of VGS. We presented it in Device Research Conference in Washington, and we found out that this was falling down below this black curve. And that was a bit problematic. Problematic in the sense that justification for working at high values of voltages, at high values of VGS becomes difficult for NSFET. Okay, this was the last work which I wanted to show to you, and maybe we'll close it after this. So what my student did was she configured using 3 structures. So what she did was she used 1, 2, 3, 4, 5, 6, 7, 8 sheets. Then you have 4, 4, and then you have effective. So it's basically ISO area. You understand ISO area? The area is always the same, so that it does not influence my current. You're getting my point? Because W by L ratio is, if you maintain W by L, whatever is the reason, I will get the same current, right? And that's the reason we made ISO area, but 3 configuration. And we found out that that D1 is this one, was giving you the least subthreshold slope, this one. But the problem with this one is it's such a long horizontal dimension. The third dimension is very, very large. Right? And that's the problem area which you will face when you do so though you get a higher switching speeds using this one, but you end up having lower reliability. Same thing happens for all these graphs as well. So that's what D1 is 8 vertical sheets, D2 is 4 vertical sheets with 2 parallel stacks, and D3 is single stack with 4 wide. So this was not our work, but by an author in TED, IEEE, and using this nanosheet PET, he was able to show the CMOS inverter VDC. I wanted to show this slide to you. The reason being that work is already started, because this is a tutorial. I just want to introduce to you, the work has already started to a larger extent in NSFETs and its circuit applications. This is again for a single stage amplifier, which is there for a single stage amplifier, which we did, and this was again from a reported paper, and what we found out or what the paper found out was that when you change the sheet thickness, right, your amplification changes, but obvious, right, because your currents will always change. When the current change, your amplification will change. Easier said than done because these are all simulation results again. So these will hold good even with fab, but typically they require a bit of refinement when you actually do a post fabrication. If you look at the gain is 2.44 here, and the gain is 6.40 when you make the nanosheet width large, and that you can understand why. When you make it from 10 to 50, you end up having a larger ion, and therefore your voltage gain V by V becomes much larger here. We are using a VDD. They are using a VDD of 65.65 volts. Okay, just touch this one because this is one of the Fox sheet. Though again, I am trying to tell you this might work, might not work. We are not very sure about it. This is a Fox sheet Fox sheet FET, which was published. The first paper came out in 2022 IEDM conference, obviously fabricated one. And what they showed in that case was that this was the FinFET, right? This was the nanosheet. What you do is that you just put a dielectric wall in the middle, which is basically a silicon dioxide wall in the middle. Once you do that, you separate out this N and P layer in two manner. So within the same area, I could have both N-type and P-type material, N-type and P-type design. What we found out was that when you do have, and this is quite interesting, since this is a dielectric wall, that's a reliability problem, which major problem will come. Since this is a dielectric wall, you do have a problem of self-heating effects. You getting my point? It is something like this. In this room, if large number of people are there is no AC working, obviously the ones who are sitting near the exits, they will feel a relatively more comfort than who are sitting in the middle. Exactly same thing happens here. Those who are near the dielectric wall, you will see a rise because they don't have any dissipative medium. You getting my point? And therefore there will be hot spots being generated. So these are hot spots being generated. And these hot spots therefore change the reliability of the device. This we used for memory design also. This was actually by one of the papers, an IEDM paper, the same NSFET. And what we saw was that in this case, the relative, so they used NSFET through a Verilog A approach and tried to formulate an SRAM, 60 SRAM cell. And then tried to find out the read margin, write margin, read delay, write delay, and so on and so forth, and plotted it across the nature. And what they found out was that if you look here, this FinFET, and that's the problem as compared to FinFET. FinFET was giving much larger, not problem with respect to FinFET. The relative read delay is relatively much higher for FinFET as compared to Fox sheet based design, right? And that is the problem area when you face when you do a high amount of scaling when you do. And typically when you push this P and N layer very close to each other, there is interference between the P and N layer, right? Interference in the sense so my NMOS switches on and it tries to switch on my PMOS also. Right? It tries to influence it. And as a result, there will be some problem in terms of reliability. My last slide with respect to maybe the CFET. And this work has actually has started around 2021, 22. CFET came into picture, and what CFET is all about is, I don't know, I have a graph here, but okay, I can show you here. CFET is, you have an NFET here, this orange one is an NFET here, and this is your PFET, right? And they are stacked one over the other. So this is the only, so you see within the same lateral area, you are able to insert both NMOS and PMOS within the same lateral area. You see, this is your P channel and that is your N channel. So you have got two N channels and you've got two P channels. You're getting my point? Now, the problem with this structure is, so there are two methods by which we generally fabricate complementary FETs. One is a sequential method and another is a monolithic method of fabrication. Both had its own advantages, relative advantages and disadvantages. But so in one case, what you do is that you grow P-FET like this, and you grow N-FET like this, and then place one over the other like this. Another is you start growing it epitaxially like this. You go on, making it till you reach the N-FET top layer metal gate. So you start with this you start with this buried VSS. This is buried VSS ground. This is your VDD. You start from here. Sequentially, you go on growing, and then you end up at the top metal layer at the top. Another one is that you do it from here, and then this part you independently make from other one, and then just flip it, sort of flip it, and place it here. Correct? So there are two methods available to us. Both had got advantages and disadvantages. Please understand, unlike Fox sheet FET, here you don't have any dielectric wall. There is no dielectric wall here, right? Now, if you look at the core area, and this is N3 FinFET, 3 nanometer FinFET, and this is my CFET. We saw approximately 25% decrement in the core area, and that's where CFET seems to be sort of maybe in next generation can work very good. This thing. Now, if you look at the relative wire length, then the relative wire length for this 60, this is an increment. So when you go from metal 0 to metal 8, 1 by 1, higher order metals gives you a much larger relative wire length in case of CFETs, because CFETs are arranged in a vertical fashion, and as a result you will have multiple wires running in this fashion, and as a result you will have always this problem of this thing. Okay, let me finally come to this slide, last slide. And what we found out was, if you plot C effective versus L effective, then as the L effective goes on changing, as the C effective goes on changing, the L effective obviously goes on increasing. Now, so this is I effective, I'm sorry, current, effective current which is there. Possibly this is a normalized, this is not a normalized one, effective value of the current. Now, now the challenges in complementary FET is, how do you not let this height go on increasing and still get the performance which you require for the device? Because if you increase the height, automatically the current increases and job is done. But when you increase the height, you also end up having reliability issues available to us, right? Sorry. So this is what we got from this case actually. Okay. So let me summarize what we learned. So I have about 1 minute to go. So I will just finish 1 minute and then we can have a discussion. So what we did, 45 minutes is not good enough to give you. I gave you a brief idea about how FinFETs have come into picture. They have already matured. What we are looking into is stacked, beyond FinFETs, we are looking into stacked nanosheet FETs. And Fox sheet FETs are coming into picture. We are again told you this might not work beyond a point. However, complementary FET might work pretty well beyond 2030, 32. We are not very sure about it. Again, all these discussions are my personal, from my personal experience, I'm saying this, right? Might work, might not work, so don't worry about it. But to the larger extent, this should, the way things are moving is, if you are those who are working in device design, heavy research will be, to my best of my knowledge, will one on materials, 2D materials. These will come up in a big way, I feel, and also on complementary effects. So let me end here is simply realizing the transistor sufficient, or must we also address about its reliability? So we need to address about reliability as well, because what I discussed with you was without any process variation, without any so vanilla flavor, everything was correct, and I was happy because that was the easy part. Professor Bagga will take the difficult part, and he will discuss with you the reliability concerns of the device, right? Thanks a lot. Thank you very much for your patient hearing.
Thank you, Professor Dasgupta. That was a very interesting lecture. I have half a mind to enroll in your classes. It was so enriching. So I just wanted to interrupt to ensure that if people have any question and any questions for you, we can take them now, and then we can have Professor Bagga's session.
Sure.
So any questions in the hall?
Oh, you have a question? Please.
Thank you, Professor. So just one question I have asked is, like, when you looked at complementary fit, I mean, I'm very new to this topic, but I'm not able to understand where the source is, where the drain is.
So the source, so there is a buried source right at the bottom, and there's a buried drain right at the bottom. So you have VSS buried and VDD buried. I showed you that slide on the left hand side. So what you do is that so basically you run this parallelly, and everything happens in middle. You drop these lines on P and N side and let it work.
So, and one more thing that you mentioned was that when it comes to this nanosheets, at higher voltages you are unable to operate at higher frequencies, but the frequencies you are mentioning is also in gigahertz, not in megahertz, right? So is it like for normal devices, let's say for a microprocessors and things, I don't think that should not be any concern.
It won't, at this stage it won't be a big problem, but the problem statement came to us from an industry source who wanted to have it for say some 5G, 6G applications, those domain areas at this stage. So they wanted to drive that whole ecosystem. So that's the reason we worked on that.
Got it. Thank you, Professor.
Good morning, Professor Dasgupta. Thank you. It was an enriching talk. Again, I would like to enroll your classes as well. Quick question. There was a hype, or I would say there was quite a bit of research on negative capacitance FET, which was also pretty dominant from last couple of years back. A group at Berkeley was working on it. What happened to that topic? Are we really looking at it?
So Saif worked on that.
Yeah.
Saif Salahuddin, and I think Saif worked, right, Navjit?
Yes.
So Saif worked on that, and NC has got not a problem, but its acceptability is still a big issue. I'll tell you why. NC for memory window applications, it might work as well. But for traditional FET applications, for example, as an amplifier or as this thing, I think CFETs are much better. Like the conventional FET are much better than NC. NC will have its application for memory. However, with current FE FET coming into picture, ferrofets, we have many other devices which are material-wise much more stable as compared to an NC. I don't think NC, I again reserve my comments, but NC is not taken up in a big fashion as it was supposed to. Maybe there is some work going on still in that domain.
Okay, thank you. One more question. I see that fork sheet and complementary fits are like competing with each other. So which one do you think would be finally, CFETs will be what is it? Okay.
CFET has got a problem that CFET, since it is vertically stacked, now the growth by itself is a very difficult to have it. So the way we do it, what researchers have done it is that either monolithic or sequential they do it. But the problem is how to, say for example, you're growing epitaxy, like growth, no problem. But if you grow it like this and then you place it like this, then if it is shifted in this manner and this manner, then there will be extra cap loading will be there. There will be a problem of less amount of current will be flowing and so on and so forth. So the very fact that you want to gain something will be offset by that process fabrication. So I'm not very sure if the process fabrication is that mature to handle at this stage. But what I'm hearing is that it will work, at least what people are, various conferences and various fora, people are saying by 2030 to 32 is the time when you will actually see CFETs possibly coming into picture.
Thank you, sir.
Yeah, okay. We'll take one last question. Okay.
Thank you, Professor, for your enriching talk. Two questions. So what is the roadmap, short-term and long-term roadmap for this nanosheet FET? And the second one is, who are the leaders in the industry driving this growth?
Okay. Short term is FinFET matured. FinFET is working fine. You can please sit down. FinFET is matured and FinFET is working fine. Challenges are there. So FinFET is surely going to stay for the next 5 years for sure, 5 to 7 years. Next in line is $1 million question, whether we'll go for fork sheet or CFET. My take CFET, and till FinFET finishes, maybe CFET will take over in the longer run. However, please keep in mind, as I discussed in the last statement of mine, good amount of work is also going on in 2D materials. So the channel, so you might have a bulk MOSFET coming into picture. Back again, that old bulk MOSFET will come into picture, but the material will not be silicon, it will be a 2D material. So the all disadvantages of the short channel effects will be lost, and you can actually scale it down to very, very low values. So that is also happening is possibly happening. As far as industry is concerned, I don't know if somebody industry people are here, they can actually tell me, but I think Intel is working on it, IBM is working on it, and GF is working on it, yes. GF is working on it. GF Dresden for sure, I know.
Thank you, Dr. Dasgupta. So we will continue with the next part of the lecture by Dr. Navjeet Bhatt.